See this question. Why do we use a laser source while recording Raman spectra? To provide answer for this question, you should be familiar with the Raman scattering. For that, consider an organic liquid called scatterer. When a beam of monochromatic radiation is allowed to pass through the organic liquid, a portion of the radiation is scattered by the molecules of the organic liquid. If you observe the scattered radiation, we can get two types of scattering. One is elastic scattering and the other is inelastic. If you consider the elastic scattering, you can see the frequency of the scattered radiation is equal to the frequency of the incident radiation. That means energy of the scattered light is equal to energy of the incident light. During this process, only the path of the incident radiation is changed by the molecules of the organic liquid, but there is no change in the energy of the incident light. As a result of this, you may get Rayleigh lines, and this is called Rayleigh scattering. This is unmodified lines. If you go for the inelastic scattering, here the frequency of the scattered radiation not equal to the frequency of the incident. That means energy of the scattered radiation not equal to energy of the incident radiation. You may get two possibilities. One is Stokes line formation and another one is anti-Stokes lines formation. In the case of Stokes lines, the frequency of the scattered radiation is lesser than the frequency of the incident light, which means that energy of the scattered radiation is lesser than the energy of the incident light. During this process, the incident radiation provides some amount of energy to the scatterer. Whereas in the case of anti-Stokes lines, the frequency of the scattered radiation is greater than the frequency of the incident light, which means that energy of the scattered radiation is greater than the energy of the incident radiation. During this process, the incident radiation absorbs some amount of energy from the scatterer. Anyway, only with the help of inelastic scattering, we can get the Raman lines. Therefore, inelastic scattering is essential. To get Raman lines. If you use ordinary light as a source less than 1 in 10 power 6 of incident radiation undergoes inelastic scattering. Therefore, it takes more time to get Raman lines. To solve this problem, we have to use a laser source. Laser is a highly monochromatic one. If you use helium neon laser with a wavelength of 3628 Armstrong unit, we can get Raman lines with clarity. So you go through the question. When monochromatic radiation is passed through an organic liquid, a portion of the radiation is scattered by the molecules of the scatterer. The scattering is due to the collisions between the photons of the incident beam and the molecules of the scatterer. If the scattering is elastic, the scattered radiation's frequency equals the incident light frequency. This is called Rayleigh scattering. During this process, only the path of the incident light is changed by the molecules of the scatterer, but there is no change in the energy. The scattered and incident radiations are at different frequencies if the scattering is inelastic. As a result, we may have Raman lines. If the frequency of the scattered light is less than the incident one, we can get Stokes lines. During this process, the incident radiation gives the scatterer some energy. Suppose the frequency of the scattered light is greater than the incident one, we can get anti-Stokes lines. During this process, the incident radiation consumes some energy from the scatterer. To get Raman lines, we need inelastic scattering. If the conventional source is used, less than 1 part in 10 power 6 of incident light undergoes inelastic scattering. Therefore, long exposures are required with a common source of light. However, the use of a laser, a powerful monochromatic source, has considerably reduced the time and solved this problem. Usually, a helium neon laser with a wavelength of 3628 Armstrong unit is used as a source.